Hey everyone, and welcome to this explainer. Today, we're embarking on what is honestly one of the most thrilling scientific detective stories in human history. We're going to shrink down, way down, to investigate the ultimate mystery, the hidden architecture of the atom, and a totally fascinating plot twist that changes absolutely everything we thought we knew about how matter behaves.
You know, it's the core mystery that's puzzled humanity for centuries, right? If everything around us, the screen you're looking at, the air we're breathing, the stars in the night sky, if it's all made of matter, what exactly is matter made of? For the longest time, scientists believed the atom was the absolute end of the road, just an unbreakable, solid sphere. But as our scientific detectives soon discovered, the atom was actually hiding some pretty incredible secrets.
Section 1. The Invisible Mystery Box, Discovering Subatomic Particles.
So, in the late 19th century, scientists started to realize the atom wasn't just a solid block at all. It was more like this invisible mystery box, just waiting to be cracked open. And unlocking it? Well, that took decades of meticulous detective work. In 1886, E. Goldstein spotted positively charged protons using cathode ray tubes. Then, by 1897, J.J. Thomson used similar rays to discover the negatively charged electron. But the final piece of the puzzle? That stayed hidden for almost another 40 years, until James Chadwick finally discovered the neutral neutron in 1932 by bombarding beryllium with alpha particles.
Okay, let's dive into this. Because early on, scientists had a very strange idea of how these pieces actually fit together. Right after discovering the electron, J.J. Thomson proposed his famous plum pudding model. He basically envisioned the atom as this positively charged sphere, the pudding, with negatively charged electrons randomly stuck inside it, kind of like plums or raisins. Now, it neatly explained why atoms were electrically neutral overall, but as an actual structural blueprint, it was about to be completely demolished.
Moving on to Section 2, the gold foil breakthrough.
Enter Ernest Rutherford. He decides that Thomson's plum pudding hypothesis needs to be put to the ultimate stress test. So he devises what is arguably one of the most elegant experiments in the history of science. Here's the setup. Rutherford takes an incredibly thin sheet of gold foil and bombards it with fast-moving alpha particles. Now keep in mind, alpha particles are these heavy, doubly charged helium ions. Because they're so heavy and pack so much energy, Rutherford expected them to just plow straight through the soft, mushy pudding of the gold atoms, maybe just deflecting a tiny bit along the way.
Now, what's really interesting about this is the actual scattering result. Rutherford sets up a circular screen to track exactly where those alpha particles went. And sure enough, the vast majority of them zoomed straight through the foil, exactly as expected. But a small number of them got deflected at weird angles. And then, the absolute unthinkable happened.
1 out of every 12,000 particles rebounded. They bounced straight back. Rutherford later said it was as incredible as if you had fired a 15-inch naval shell at a piece of tissue paper and it came right back and hit you. This shocking discovery totally destroyed the plum pudding model. It proved that atoms are actually mostly empty space, but right at their very center lies a tiny, incredibly dense, positively charged core that contains almost all the atom's mass. The nucleus had officially been discovered.
Which brings us to Section 3, Bohr's atomic blueprint.
So, Rutherford found the nucleus. But hold on, if electrons are just floating around out there, why doesn't their negative charge pull them crashing right into that positive center? Well, in 1915, Niels Bohr brought some much-needed order to the chaos. He proposed that electrons don't just wander around anywhere they please. They're locked into very well-defined, discrete circular paths, orbits, or shells. Each shell has a fixed energy level, and electrons can only jump between them by gaining or losing specific amounts of energy. They can literally never exist in the empty space between them. It's this beautifully ordered, almost solar system-like blueprint for the atom.
So there we had it, the neat, tidy rules for the universe's building blocks. Inside that dense, tiny nucleus, you've got your heavy protons carrying a positive charge, and your heavy neutrons carrying no charge at all. Both of them pack a relative mass of 1 atomic mass unit. And orbiting way on the outside are your lightweight electrons weighing roughly 1/1840th of a proton, practically nothing in comparison. And the atomic number, the actual identity of the element, is strictly defined by the number of protons. It was all perfectly neat, perfectly predictable. Until...
What if I told you there was a major plot twist? What if nature actually breaks its own neat little rules? Imagine, for a second, encountering two absolutely identical twins. They look exactly the same, they behave exactly the same, they even have the exact same chemical makeup.
But when they step on a scale, one is significantly heavier than the other. How is that even possible?
Welcome to the world of isotopes. This is exactly where our atomic detective story takes a really fascinating turn. Isotopes are atoms of the exact same element, meaning they have the exact same number of protons and electrons, so they look and act identically in chemical reactions, but they have a secret. They have a totally different number of hidden neutrons right there in their nucleus. This means their atomic number is completely identical, but their overall mass is different.
Let's just look at the simplest element in the universe, hydrogen, to see this in action. Hydrogen has one proton, but it actually exists in 3 distinct weight classes. Protium, which is the most common form, has 0 neutrons. Deuterium, a heavier isotope, has 1 neutron, and tritium, the heaviest of the bunch, packs in 2 neutrons. They're all hydrogen. They all react exactly like hydrogen, but deep down inside the nucleus, they're carrying entirely different atomic baggage.
Let's move to section 4 and see how this builds into something practical: isotopes in daily life.
Because we really need to build a bridge from theoretical quantum physics directly into our daily, macro-level lives. Having a few extra neutrons isn't just some fun trivia fact for a science test. It has literal, world-changing consequences. You see, when a nucleus crams in too many or too few neutrons, it can become unstable. It desperately wants to reach a stable state, and to do that, it decays. It literally throws off its excess energy by emitting powerful alpha, beta, or gamma radiation. We call these radioactive isotopes. And humans, being as inventive as we are, have learned to harness this incredible atomic anomaly.
So the crucial point here is that these unstable isotopes have become some of the absolute most powerful tools in modern science, medicine, and energy. We use uranium-235 as the fuel of choice to generate massive amounts of electricity in nuclear power plants. In the medical field, they're absolute lifesavers. Cobalt-60 is famously used in radiotherapy to target and treat cancer. Phosphorus-30 is used in the treatment of leukemia. And iodine-131 acts as this brilliant tracer. You inject it into the body, it goes straight to the thyroid gland, and it allows doctors to diagnose and treat diseases like Goitre. Which leaves us with this final, awe-inspiring thought to reflect on today. Our journey started by trying to crack open a solid, invisible box. And what we found was this incredibly dynamic, structured universe, where something as tiny as a single, neutral subatomic particle, just a simple neutron, can completely transform a harmless element into a powerful, energy-yielding, life-saving tool. It really makes you wonder, what other invisible secrets is the universe still waiting for us to uncover? Thank you so much for exploring the atom with me today.